Welcome to this video, Unit 2 of Essentials of Calculus. In this video, we're going to talk about calculating limits, and we're going to discuss some continuity. In this lesson, there's going to be 3 split videos, so you want to watch all 3 of those. And let's go ahead and get to it. The first topic that we're going to discuss is limits. Now, if you have a function that is continuous at a certain value, you can go ahead and evaluate a limit algebraically with direct substitution. Now, there are some cases where we're going to have an indeterminate form. Okay, here's this word, indeterminate, right? You cannot determine. Okay, and the form we're going to discuss in this lesson is 0 over 0. Okay, there are other forms, and we'll get to those later on in the course. However, we're going to specifically talk about this one. So we'll jump right into an example here where we're asked to calculate the limit of x over x times x plus 1 as x approaches 0. So if I plug in 0, notice that this is going to go to 0 over 0. Okay, so that's not good, right? I cannot be determined. The limit cannot be determined. So what we're going to do is we're going to simplify or reduce, and you want to reduce a denominator usually. So x reduces with x, and now we have the limit as x approaches 0 of 1 over x plus 1. Okay, so now if we go ahead and evaluate, now we get 1. Okay, it's important to note too on the AP test, when you get this indeterminate form, you do not want to leave the 0 over 0 up here, right? So make sure you cross out this work. If on the AP exam, if you don't want work to be graded, cross it out. Okay, so we'll make sure we'll cross those out. Now, I just want to discuss what's happening here at 0. Remember from Accelerated Math 3, if we reduce a factor top and bottom, what we have is a whole. So if I take that x value, okay, and I set it equal to 0 and solve, we get the value, okay, of where that whole exists, okay, and in this case it is 0. So I'm going to write over here to the side. Because of this, we have a whole at 0, and then the output in this case, right, didn't we evaluate this function at 0, and the output was 1, so we have a whole at 0 comma 1. Okay, so let's look at example number 2. In example number 2, again, we'll plug in 2 into our function, or our relation here, x minus 2 over x squared minus 4, okay, and what we get on top is 0, and on the bottom we get is 0. The limit cannot be determined. So I want to cross that out, and what I want to do is I want to reduce a factor top and bottom. Now you'll notice that I can't reduce anything right away, so what we have to do is we'll want to factor. Okay, so the limit as x approaches 2 of x minus 2, and in the bottom we have x minus 2, x plus 2. Okay, now I can reduce. X minus 2 is reduced, and this gives us the limit as x approaches 2 of 1 over x plus 2. And now if we evaluate with direct substitution, we get 1 over 4. Okay, so that would be our limit as x approaches 2. Again, if I want to know, okay, what's happening here, right? I have another whole, a removable discontinuity, if you will. We discussed that in the last video, 1-4, at 2. Okay, and that output 1/4. Okay, so there's a hole there. All right. Example 3. Here, in this case, we plug in 1 into our relation x cubed minus 1 over x minus 1. And on top, we get 0. On the bottom, we get 0. Okay, so again, I'll cross this out. And what we want to do is we want to factor Okay, and what we're going to do for the top, this is difference of cubes, so we're going to use the difference of cubes formula, x minus 1 times x squared plus x plus 1 over x minus 1. All right, so we're going to go ahead, we will cancel, x minus 1s cancel top and bottom, and we get the limit as x approaches 1 of x squared plus x plus 1. Now, it's important to note that you keep your limit notation. Notice how through all of these examples, I've kept that limit notation. Now, I know you're signing going, ugh, I don't want to write that. I just want to say that this piece here is equal to x plus 1. That's not true, okay? And if you write that on the AP exam, you may not get the point, or you may not be eligible for further points, and we don't want that. So whenever you're saying that this limit is equal to this limit, right, you have to keep that notation going. Okay, so I'm going to go ahead, I'm going to evaluate this polynomial now, x squared plus x plus 1 at 1, and we get 3. Okay, and I'll write again right here, right? We have a removable discontinuity. We have a whole at 1, 3. Okay, so where are these values coming? These values are coming from, again, here, your x value and your output, right, which is 3. All right. Moving right along, now we get to number 4. Number 4 here is tricky. So notice in the numerator we have the square root of x minus 1, and in the denominator x minus 1. We'll plug in 1, so this gives me the square root of 1, which is 1. Take away 1 on top, we have 0, and in the denominator we also have 0. So I want to factor this after I cross out that 0 over 0. Okay, so how are we going to factor this to cancel? Well, one way to do this is to factor your denominator here using the difference of squares. So I'll write this here. We have the limit as x approaches 1, square root of x minus 1 over, okay, difference of squares. So the square root of your first term minus the square root of your second term times the square root of your first term plus the square root of your second term. Okay, and again, if this looks weird, just remember, what is this factored? Isn't this x minus 2x plus 2? Okay, the same idea going on here. So we can reduce, right, giving us the limit as x approaches 1 of 1 over the square root of x plus 1. All right. Okay, and this gives us 1/2. Okay. So, sorry for that. My computer's acting up. Okay. And again, we have here, we have a whole at 1, 1/2. All right. I guess I'll show you guys this too as well. The other way to factor this, whenever you see a square root minus 1, another way to take care of this is if you multiply by the conjugate. Okay. X plus 1 on the top over square root of x plus 1 in the denominator, so I'm not really changing it, right? Multiplying by 1. So in the numerator, what you'll end up with is this will go to x plus 1. Sorry, x minus 1. X minus 1. Okay, and then that will cancel out with your denominator, and you'll be left with what we have here, 1 over x plus 1. Okay, so that's another method that you can use. All right, moving on to example 5. Example 5 is different. In this case, if we evaluate this limit at 2, in the numerator, we will obtain 2, and in the denominator, we will obtain 0, 2 over 0. So this is undefined, right? 2 divided by 0. So what we get is that the limit does not exist. The limit, and I don't even know if I want to put equals there, we just say limit does not exist. Okay, and when a limit does not exist, you'll get two cases. You'll get negative infinity or positive infinity. Okay, so in order to determine, right, sometimes they'll ask you what type of, or where does the function approach, right, for a does not exist. So I want to know, is it going to approach negative infinity or positive infinity? And what we'll do here is we'll do sign analysis. Okay, and what I'm going to do is I'm going to go ahead and the top, right, if I plug in 2, do you agree that that is positive? And in the denominator, if I take a number, okay, we're coming from 2 from the right. So imagine I'm taking 2, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. Okay, and if I take that number and I subtract by 2, you agree we have a positive value. So a positive divided by a positive will always produce a positive. So therefore, right, this function, the limit is approaching positive infinity. Okay, and what's going on here is that we have a vertical asymptote, right? This is a non-removable discontinuity at x is equal to 2. Okay, and from the right side, right, my function is approaching positive infinity. Okay, 2 more examples. Here we're going to talk about continuity, and they're asking us to discuss the continuity. I want to recall your prior knowledge on continuity, that a function is continuous if the function value, if f of x is equal to the limit of f of x, okay, as x approaches that value. Okay, so I want to say as x approaches x. I mean, whatever value. And actually, maybe we want to adjust this notation wise. Let's make this f of c. Okay, so and we'll look at an example here. So looking at number 6, it says discuss the continuity of f of x, and this is a piecewise function. Note for x values, when they're not equal to 3, we're going to use this rational function, and when x is equal to 3, we have an output of 5. Okay, so what I'm going to do is I'm going to go ahead and factor this. So I have x minus 3, x plus 1, sorry. Okay, and our x minus 3's cancel. Okay, so here's our new function. F of x is equal to x plus 1 when x is not 3, and 5 when x is 3. Okay, so what I want to determine here, right, according to our definition of continuity, is my function value, f of a certain value, okay, is it equal to the limit of that value? So I'm going to evaluate my function at this breaking point here, 3. So what is f of 3? Well, if I plug in 3 into my function, I get 5. So this is equal to 5. Now what I'm going to do is I'm going to evaluate what is the limit as x approaches 3. Okay, and I'm going to do it from the right. Okay, so when I plug in the value, okay, I'm going to get 3 plus 1, right? So 3 plus 1, which gives us 4. So notice, right, that the limit, okay, does not equal, let me change this to x, notice that the limit does not equal, okay, the function value. So therefore, we have a removable discontinuity here. Okay, so since f of 3 does not equal the limit as x approaches 3 of f of x, okay, we can say f of x has a removable discontinuity at x equals 3. Okay, so that's discussing the continuity of the function. There's a removable discontinuity. All right, number 7. So number 7 also looks different too. You'll notice that we have multiple variables here, and it says if g of x is equal to this piecewise function, and it is a continuous function, find the value of a. So since it is a continuous value, what we're going to go ahead and do is we're just going to plug in the cut point. So plug it in, okay, and what we get is 3 times 2 squared plus a. This will be equal, right? If it's continuous, I know that these values, right, I'm not going to have a break, okay? So at these 2 points, these should be equal, okay? And on the left side, we get -1. On the right side, we get 3 times 4, and we solve. Okay, and therefore, that's pretty ugly, 3, okay. We get a is equal to -13. All right, so in this video, we talked about calculating limits in where we find a indeterminate form, and how to reduce our rational functions and evaluate the limit. And we also talked about continuity of different types of functions. Okay, go ahead, watch the next 2 videos. We'll talk about using a calculator, and then we'll talk about the IVT in the 3rd video.